World Health Organization (WHO) statistics show that more than 4.9% per 1000 persons working in the factories suffer a loss of arm. The main aim of the project has been to provide a solution which will address the basic problems these people face.
This project is submitted as a part of Texas Instruments India Analog Design Contest 2011. The project entitled Wireless 3D Robotic Arm with Force Quantification using EMG. Coming to the Texas Instruments products used: ARM processor LM3S3748, CAN processor LM3S2965, dual operational amplifier LM358N, and the multiplexer SN74HC153. The non-Texas Instrument products used are Zigbee for transmission and receiving, manufactured by Digi International; servo motors, manufactured by Next Robotics as well as High-Tech HS311; accelerometers, manufactured by LubDub MMA7361L; surface EMG electrodes, manufactured by LubDub. This is the ground electrode and this is the surface active electrode.
This is the flex sensor. Then we'll move on to EMG filter and amplification circuit. This is the filter circuit. Then this is the flex sensor. We'll explain you about different modules now. Let us start with flex sensor. Flex sensor is nothing but the resistance value can be converted into voltage value. So you can see the variation in the voltage. When you bend your fingers, you can see the change in voltage, increase or decrease in the voltage. So the flex sensors are also called force sensor, and that's how we finally achieve the quantification of force, wherein the proper grasp of the object in the robotic arm is achieved. So you can see the variation in the voltage. When you bend it, the voltage is increased, and when you re-stretch it, the voltage is being decreased. This is the main advantage of the flex sensors. Next module is about EMG electrodes. Basically, EMG electrodes or maybe needle or surface electrodes. For convenience, we are using surface EMG electrodes. When there is no activation of the muscle, the voltage waveform you see in the DSO is uniform. When you give a small excitation to your muscle, here we are giving excitation to the biceps. So whenever you give small excitation to the biceps, there is a sudden peak in voltage or rise in voltage. When the activation is prolonged for some certain time, the change in the peaks is continuous. When you again relax it, automatically the wave is getting relaxed. So the EMG signals, we are storing it, and the peak values are being given to the ARM processor. So you can see the continuous change in the voltage when the biceps are being stretched. You can see the waveform has again become uniform when you again relaxed. You can even place the electrodes to the forearm or wrist. Now we'll see the accelerometer module. Basically, accelerometers are used to track the voltage based on the positions of the human arm. As we see, accelerometer gives the linear variation with the angle of the rotation. So in the graph of the DSO, you can see the variation of the voltage when the accelerometer is tilted either clockwise or anti-clockwise. Next, we'll see the analog to digital conversion. The analog voltage generated by the accelerometer is converted to digital form. This is given to the hardware module to generate the pulse width modulation which is required for the functioning of the servo motor. There you can see the change in the values. When you tilt the accelerometer, you can see the change in the value there. Next, now we'll demonstrate the working of the prototype. You see the flex sensor there on the accelerometer. You can also see the surface EMG electrode, that's basically the ground electrode, and there on the biceps you can see the active electrodes. So on tilting the hand, that's when the motion is changed, you can see the variation in the pulse, variation in the voltage. So this is the main circuit, total circuit. You are seeing the filter circuit, and you see the regulated supply readings, current and voltage. So simultaneously you can also observe the motion of the robotic arm, which is almost imitating the motion of the human arm. Here you see the motion of the human arm. As proposed, we are showing you the three-dimensional motion of the human arm. You can see how the robotic arm is imitating the human arm. We finally say a sincere thanks to the Texas Instruments team, especially CP Ravikumar sir and Juneja Sagar, for guiding us throughout the competition. Thank you.